I am Jyoti Sharma once again in front of you with the topic of Aktu University question paper solution, and we'll be discussing the solution of section B. As in the previous lecture, we have discussed the solution of section A, the complete 7 questions, which are the short questions having 2 marks each. Now we are going to discuss section B, and if the time permits, section C will start. Okay, moving on onwards, the subject as we were dealing was fundamentals of electrical engineering, having a subject code of BEE 101 under AKTU. Now, in the university question paper, the section B is having a second question, A part, as using nodal analysis, find the branch currents in the circuit. For the circuit shown here, we need to find all the branch currents using nodal analysis. Fine. For this particular circuit now, the steps for solving nodal analysis is, first we need to go for all the nodes, or I must say all the junctions which are occurring in this particular network, right? So if at all I see how many junctions are occurring in this particular network, so those would be, this is node 1, considering the potential at node 1 as V1. This is node 2 or junction 2, considering the potential at this junction as V2. And the third one is V3, which is supposed to be at ground potential or at zero potential, right? So first we have identified the number of junctions. Then we have allotted the junction voltages as V1, V2, V3. Out of that, V3 is known. We are considering it to be as the ground potential so that all the currents are flowing towards this particular junction. Fine. If that is so, now we'll be applying KCL at the remaining 2 junctions. Fine. So if we apply KCL at junction 1, applying KCL at junction 1, right? So if at all I see here, do I need to have to write the KCL equation for this? Don't I know how much is V1? If you just see here, V1 is the junction here and the voltage across this junction itself is 6 volts. So I need not to write even the KCL equation for this particular junction. I directly know that the voltage at junction 1 is 6 volts. In another case, if at all, this would not have been a voltage source, this would have been a current source or a resistance, then in that case, I need to apply the KCL at this particular junction, like we are going to do it for junction 2. That means, now for knowing the equation for this, we need to apply KCL at junction 2. Fine. Right. Consider the currents. Say I am considering this as I1, this as I2, this as I3. Considering that the potential at junction 2 is at highest, that means V2 is greatest of all. If V2 is at highest potential, I am just considering, I may be proved wrong later on, but if at all I am considering that V2 is at highest potential, then all the currents will be moving outward from this particular junction, right? That's why I1, I2, I3, I have considered all the currents to be assumed, in fact, all the currents to be moving outward. I may be proved wrong later on. Fine, if that is so, I may be writing that I1 plus I2 plus I3 must be equals to 0. As we know, for a KCL, the sum of all incoming current must be equals to sum of all outgoing current. At this particular junction, there is no incoming current. For easy solving or for having an easy equation also, we used to assume that this is at highest potential so that all the currents are moving outward, and the equation is as simple as that the addition of all the currents is equals to 0. Fine. How can I write the equation for now? I1. The I1 can be given as, it is flowing from V2 to V1. So V2 minus V1 upon the resistance 2 plus I2. I2 is the current which is flowing in 12 ohms. That must be given by V2 by 12. And lastly, I3. I3, now for particularly this, it is itself a current source, right? A current source of 4 amperes. It means that in this particular branch, we already know how much is the current flowing. That is 4 amperes, that too in the upward direction. And the direction considered by us is the downward direction. That means it has to be minus. So it will be minus 4 is equals to 0. Right? Solving this equation, Once again, V1 we know. What is V1? V1 is equals to 6 volts. So substituting V1 as 6, this becomes V2 minus 6 upon 2 plus V2 upon 12 minus 4 is equals to 0. Solving the equation will get V2 as 12 volts. Right? So V2 is 12 volts, V1 is 6 volts. Now we got both the voltages. This is 6 volts and this is 12 volts. Right? Now we got the junction voltages. Now the next thing required is to find the branch currents in the circuit, right? So let's move on with the branch currents. Say, how much is the current in I1? That means the current in the branch 2 ohms. That means the current in 2 ohms. That can be given as, if you just see, V2 minus V1. This is 12 minus 6. So it is 12 minus 6 upon the resistance 2. So this is 12 minus 6, 6 upon 2, that is 3 amperes, and the direction would be towards left, from 2 to 1. Fine. Now I2, the current in 12 ohms. The current in 12 ohms is V2 by 12. V2 itself is 12, so 12 by 12, that makes it 1 ampere, and the direction would be downward, right? I3 we know it is directly minus 4 amperes. We know the current which is flowing in the third branch, and we know that it is going to be 4 amperes, right? So it will be, in fact, I should be writing it as 4 amperes. I should mention the direction that the 4 amperes would be upward, okay? Then what is the remaining one? The current flowing in this 3 ohms, right? So the current flowing in this 3 ohms would be given by, in this particular case, the current flowing in this 3 ohms would be given by V1 upon 3. V1 is 6, 6 upon 3 is 2 amperes, and the direction of the current would be downward. So these would be the currents in the various branches of the circuit, and that we have solved using nodal analysis. Moving on with the second B question. Derive mathematically the dynamic impedance offered by RLC parallel circuit under resonance, and also draw its phasor diagram. Right. So it is an RLC parallel resonant circuit. There are various circuits for the parallel resonance, but the most common tank circuit which is being used for this parallel resonance circuit, that is an R and L connected in series, and that is connected in parallel with a capacitor that is being fed with an alternating supply, say V. The total current which is flowing is, say, I total. The two currents in the inductive branch, in the capacitive branch, this is R, L, C. I may be just designating the impedance for this as ZL, right? And ZL is some R plus JXL, fine. For this tank circuit, now, if at all, I want to derive the dynamic impedance. That means the impedance which is occurring at the state of resonance. Now for the parallel resonance circuit, we know what are the characteristics for a parallel resonance circuit. That first of all, its power factor is going to be unity. That is the first. And for making power factor unity, we will be just deriving what will be the conditions and what is going to be the impedance. We will be seeing that at the state of resonance, the impedance of this parallel resonance circuit and would be a combination of the dynamic components, right? It will not be changing, it is a constant value, it is the maximum value, but it is composing of the dynamic elements. Opposite, unlike to the series resonance circuit where at resonance condition, the impedance would be minimum and its value is only R, right? But in case here, we'll be seeing that it is depending upon L also, it is depending upon C also, which are the dynamic components. Fine. So now, if at all I represent all these parameters which are over here, voltages and currents, in phasor diagram, as the phasor diagram is also being asked. So, we can be drawing the phasor diagram keeping voltage as the reference, because voltage is the quantity which is common to both the branches, right? So we'll keep voltage as the reference, fine. then where should be IC? IC is the capacitive current, and for a purely capacitive circuit, the current will lead the voltage by 90 degree. So IC should be leading by 90 degree. Now what about IL? IL is the inductive current flowing in an RL circuit. So for an RL circuit, what used to be the nature? That the current would be lagging the voltage by certain angle phi. Not by exactly 90, but by certain angle phi. Right? In fact, I am writing it as phi L, because phi represents the complete power factor of the circuit. Phi L is the power factor for this RL circuit. So it will be lagging by certain angle phi L. Now, if at all I want to have the condition for the resonance. So one thing I know, that at resonance, the power factor of the circuit is going to become 1. That means the total current taken by the circuit and the voltage, supply voltage, are going to be in same phase, right? Looking at the phasor diagram, what can be the possible condition? That the total supplied current, which is the phasor addition of IL and IC, which has to be the phasor addition of IL and IC, that should lie in phase with the voltage. What should be the condition? So we can see I can resolve IL into 2 different components, right? As this is phi L, I may be having 2 components. One is IL sin phi L and another one is IL cos phi L. So if at all this becomes that IC is equals to IL sin phi L, these two will cancel out each other and I'll be remaining with just IL cos phi L, and that will be the total current taken by the circuit, and that is in phase with the voltage. So these two are the conditions which will satisfy our resonance condition, right? So for resonance, parallel resonance of this tank circuit, the condition should be that IC should be equals to IL sin phi L, and another one, the total current should be equals to IL cos phi L, right? Now, we got the conditions, we got the phasor diagram, we got the conditions. Now, how can we have now the dynamic impedance? To find the dynamic impedance, we'll concentrate on this condition, right? What is the condition? The condition, the second condition what we see is the total current in the circuit is equals to IL cos phi L, right? Just see this triangle, right? I'm just reforming it. This is the triangle giving me phi L. Can I draw the impedance triangle for this, for the same phi L, right? If at all from the same triangle, if at all I draw the impedance triangle, the parameters what I'll be having it is R, this will be XL and this would be ZL. Am I correct? Because this is the one which is corresponding to only RL circuit, only to phi L, right? Not for the complete circuit. So it is going to be R, this is going to be XL and this is going to be ZL. Fine. Now, just going with the equation that I is equals to IL cos phi L. Now once again, how can I write IL as? I can write IL as V upon ZL, can I, from the circuit? IL can be given as, because this is parallel circuit, the voltage across both the branches would be same. So it is going to be V upon ZL, okay, multiplied by cos phi L. So cos phi L is given by, from the voltage triangle, it is given by R by Z. So it is R by ZL. So this becomes VR by ZL square, right? And we have seen that in the earlier case, if at all I go with the condition that IC is equals to IL sin phi L, if at all I derive the condition from here, we can be in fact IC is given by V upon XC. Can I write this? IL is once upon V upon ZL, and sin phi L. Sin phi L is given by XL by ZL. So once again, if you just see that ZL square is given by XL into XC, which is L by C. ZL square is L by C. So just substituting here the ZL square as L by C again V upon L upon, I am taking R downside, that becomes L upon RC. This is all we are doing for I, right? So I is equals to some V upon L upon RC. What should be this term? Current is equals to voltage divided by impedance. And this is all we are doing at resonance. So that means this is going to be the impedance at resonance state, which is going to be the dynamic impedance, what we call it as the dynamic impedance, which is the maximum impedance offered at the state of resonance, right? So the expression for the dynamic impedance becomes L upon RC. The expression for the dynamic impedance is Z is equals to L upon RC. Okay, now moving on with the C part, which is, what is the purpose of an equivalent circuit of transformer? Obtain the approximate equivalent circuit of the transformer as referred to primary with all the necessary parameters. Fine. So what is the purpose of equivalent circuit of the transformer? Why do we go with the equivalent circuit, or why do we study it, right? So the equivalent circuit of the transformer is very much required. It becomes very feasible with the equivalent circuit to find the mathematical modeling, to go with the transformer, to find the losses in the transformer, to find the efficiency of the transformer, the voltage regulation of the transformer. That means to find all the performance parameters of the transformer, this equivalent circuit becomes very important. It plays a very important role because if we don't have the equivalent circuit, we don't have the parameters. We don't know how much is V1, I1, how much are the no load parameters, how much is the no load resistance or the reactance, right? So with the equivalent circuit, this becomes very feasible. In fact, with the equivalent circuit referred to primary in circuit, this becomes even more feasible because we don't have to calculate the two side, we don't have to go for the two calculations for primary side and for the secondary side. One equivalent circuit is available with us, and within a single circuit, we can apply our KVL, KCL, or we can apply any mathematical modeling for a single circuit to find out the performance parameters of the transformer. So this is the purpose of having an equivalent circuit of the transformer. Now, how can we give this equivalent circuit of the transformer as referred to primary? Now, when referred towards primary, that means the primary parameters are not going to get changed, right? So the primary parameters are going to remain same, starting with the supply, which is an alternating supply, say V1, right? Then the input current, that is I1. Then we are having the input current is I1. Now, in approximate equivalent circuit, we deliberately make a change that we used to get the no load circuit prior to R1X1, right? In fact, the no load circuit is after R1X1, after I1, but deliberately for an approximate equivalent circuit, we deliberately create an error so that all the resistance is towards one side and all the reactance is towards one side. And that is being given, this is the no load current. The no load current is flowing in, will be divided into two parts. One is IM, magnetizing current flowing in XM. Another one is IW, the working current flowing in R0. And then we are having the primary resistance R1. Then the primary leakage reactance X1. This is up to the primary circuit, right? Now the secondary parameters are referred towards the primary circuit. Now when we refer the secondary parameters, likewise R2 dash towards the primary side, its value is changed to R2 dash, and that is given by R2 by K square. Similarly, this is x2 dash, which is x2 by k square. What is k here? Where k is the transformation ratio of the transformer. K is the transformation ratio given by V2 by V1, given by N2 by N1, given by I1 by I2. Right? This is the transformation ratio. Now is our load, that is ZL dash, given by ZL by K square. The terminal voltage V2 dash, that is given by V2 by K. The current flowing here, that is I2 dash, which is given by K times of I2. In fact, minus of K times of I2 in phasor, right? Now what we can do here, this R1 and R2 dash, these can be combined to give the equivalent resistance referred to primary R1E. Similarly, X1 plus X2 dash give us the equivalent reactance referred towards primary, that is X1E. And combiningly, we can have Z1E given by R1E plus JX1E. Right? So, this gives the approximate equivalent circuit. In fact, the induced EMF E1 and E2 dash, which is given by E2 by K. This was also remaining. The induced EMF we need to represent, right? So the primary parameters are there as it is. Only the second parameters are being transferred towards the primary, referred towards the primary side with the changed values, right? This is the approximate equivalent circuit. The calculation becomes very easy when it is referred towards one side. The complete circuit is towards either primary or towards the secondary. Now, moving on with the deep part, what is the magnetic material? Write the type and explain it. So, a magnetic material, if at all I say, which inhibits the magnetic properties, right? What are the classification? So, the classification we are having the diamagnetic, the paramagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. If at all I go with the diamagnetic, so these are the materials which lack the permanent dipoles, right? Whereas the paramagnetic, they do not interact among themselves. The dipoles, the permanent dipoles, they do not interact, right? And the ferromagnetic, the interaction among the permanent dipoles is strong, and all the dipoles that line up in parallel and the material is ferromagnetic. Antiferromagnetic, if the permanent dipoles, they line up in the anti-parallel direction, right? And ferrimagnetic, if the anti-parallel with, they align themselves in anti-parallel direction with unequal magnitude. Specifically, if at all I go with the diamagnetic, paramagnetic and ferromagnetic, so for the diamagnetic material, if at all I say, these, there is no permanent dipoles which are present to, so that the net magnetic moment, that is zero, right? Neither by the spin, so that the net magnetic moment is zero. So the dipoles are induced in the material in presence of the external magnetic field only. The magnetization becomes zero on the removal of the external field. When you remove the external field, the magnetization becomes zero. The magnetic dipoles in these substance, they tends to align in the opposition to the applied field. The magnetic susceptibility is very small and also negative. The important thing is their relative permeability is less than 1, right? If at all I go with the examples, so we are having mercury, we are having water, we are having gold, we are having diatoms like H2 and N2, right? Now the paramagnetic ones. So these are the materials in which the magnetic dipoles, they tend to align along the applied magnetic field, and thus they enforce the applied magnetic field. Such materials, they feasibly magnetize in the presence of the magnetic field, and the magnetization disappears as we just remove the external field, right? So the orientation of the magnetic dipoles, they depends upon the temperature and the applied field as well. The relative permeability is greater than 1, but it is not significant, but they are greater than 1. Then susceptibility is also once again small and positive. The materials which are generally being used are generally liquid oxygen, sodium, platinum, right? The salts of iron. The ferromagnetic materials. So these are the materials which are in fact of much interest to us. So they exhibit the strongest magnetic behavior, right? and the permanent dipoles are present, which contributes a net magnetic moment. So when they are placed in the external magnetic field, they strongly attracts the magnetic lines of forces. And the magnetic field of these material, they persist even when the external field is removed or when it is disappeared. So this property is used to produce the permanent magnets, which are generally being used in the machines. The transition metals like iron, cobalt, nickel, and their alloys are usually used for the ferromagnetic material. This is susceptibility is positive as well as large. Now the E, the last point, the question, that is, what do you understand by earthing and neutral grounding in electrical wiring, and discuss the importance of earthing. So if we say what is the difference between earthing and neutral grounding. So basically earthing, it is the method which protects the human beings as well as the personnel which are working from the electrical shocks, right? But grounding is a method which protects the entire power system from the malfunctioning, right? Earthing means we are physically actually making the potential zero. We are making it earthed, right? But grounding is making all the voltages to be at the zero potential, right? So the earth wire which is used, that is generally green in color, and the wire which is used for the grounding, that is black in color. Earthing is primarily used to avoid the electrical shocks, whereas the grounding, that is primarily used for unbalanced, where the electrical system overloads is there and unbalancing there. It is generally being used at the unbalanced system to get it balanced, right? And earthing is located under the earth pit where the equipment body and the underground pit is there, whereas the grounding is located between the neutral of the equipment being used and the ground, right? So because the neutral of that particular equipment is being grounded. Now, why earthing is required? What is its importance, right? So when it is being considered for the electrical appliance or for any installation or for any building as well, so it protects us from the danger of electrical shocks resulting from the short circuits or even the overloads, even the unbalanced, because one of the way of earthing is also neutral grounding. So it offers an easy path for the current of the short circuit to flow even after the insulation get failed. The earthing saves the equipments as well as the personal working from the lightning discharge and voltage surges. It protects the installation and the working personnel from the fire hazards. These are the certain important aspects of earthing. Once again, we'll be continuing on with the next session for the same university question paper solution, continuing with the third question and fourth question for 23-24 even semester question paper, university question paper. Thank you.